pleasure to introduce the final speaker for today's sessions. And I want to just introduce this with a little bit of history about the NPA. I'm sure some of you are from Tesla Tech, probably never even heard of the NPA until a few hours ago. And we want to make a welcome to you especially. But I want to just tell you a little bit about our history. This organization was founded, this is our 19th annual conference, so it was, the first conference was held in 1994. And the man who organized this organization, the Natural Philosophy Alliance, is named John Chappell. He wrote a paper which I introduced 2 days ago in my talk, in 1965, about the Sagnac effect. And he made the observation that a lot of what we think we know is, about physics is based on a misunderstanding of the foundations of those things, the very metaphysics behind that. And so that's really kind of the underlying principle behind the NPA. And I never had the chance to meet Dr. Chappell. He died in 2002. But his ideas and his ideal for an organization that could get together and discuss ideas openly on the foundations of science is really a great one, and it's what led to us being here today. And so in recognition and in honor of Dr. Chappell, we had, in 2004, our organization instituted a special presentation once a year that would be in his honor. And so this year, the next presentation is to be that presentation. And I don't know if you recognize this, it just kind of hit me today that, do you realize that we have the world's foremost authorities on several topics right here in this room? And the world's authorities on electric universe concepts, the world's authorities on electrodynamics, the world's authorities on Einsteinian physics are here in this room. And we also have with us the world's authority on perhaps one of the most interesting and fascinating experimental concepts right now, and that is cold fusion, or known as cold fusion. Today we like to call it low energy nuclear reaction. And we have a man who was involved in this event, and I'm sure he'll be telling you a little bit about the history, so I won't go into that. But he's been involved from the beginning in 1989 and has been active at Los Alamos Laboratories, not too far from here, doing experimental work in this area, and probably knows as much as anyone about this. From the beginning, he was, I have the very first version, issue of a magazine that was called Cold Fusion, which was the predecessor of Infinite Energy magazine, and the man that was on the cover of that magazine is our next speaker. And so it's really a great privilege. I feel that this is, we have in our presence the world's authority on what's going on in this. And he's going to speak today not only about the history and how this all we got here today in this exploration, but he's going to tell us a little bit about the science behind it and really giving us an explanation for an experimental fact that is undeniable. It's been reproduced many, many times. And so it is a tremendous honor for me and a great thrill for me to introduce to you Dr. Ed Storms.
Thank you, Greg. Before I answer your questions, I'd like to ask you one. How many of you believe that cold fusion is real? Please. Oh, wow. It looks like the skeptics are outnumbered. Just to remember and to carry away with you when you leave. So you don't have to stay awake for the whole talk. And if you believe what I want you to remember, that's even better. Elian or cold fusion is a real phenomenon that's able to initiate various nuclear reactions by a unique process. That's basically the claim. It isn't just a single nuclear reaction, but it's a group of nuclear reactions. The Elian process has no relationship to hot fusion process other than that the fusion of hydrogen isotopes is involved in both cases. The problem early in the field was the effort to make a relationship between the two, because cold fusion did not act like hot fusion. In some people's mind, cold fusion could not be real. The fact is that they are entirely different phenomena operating under different conditions, and we'll look at that in more detail. So try not to apply what you have learned about hot fusion to cold fusion. The third thing is that LNR is the most important discovery of the last 2 centuries, with applications to energy production and the understanding of nuclear behavior. That's very important, because LNR, or low-energy nuclear reactions, are a source of energy. We are in desperate need of energy. We're at the present time polluting the environment, risking runaway heating of the earth, endangering the food supply, and even risking nations when accidents happen. Now, you'd think that if somebody came up with a way of making an ideal energy source, a source that has no problems, no pollution, no CO2, that they would jump at the chance to investigate it, even if it was improbable. And so you have to ask why. It's been more than 22 years and counting that this particular phenomena has not been accepted by the ordinary scientists and by technology. Well, the reason for that is that a myth was created. Now, if you want to censor something, all you have to do is create a myth, and then all the people without imagination and who are lazy will do your dirty work. But this myth was created, and the myth essentially says it's an impossible process proposed by people who are deceived and stubbornly insist they are right in spite of obvious errors. That's a universal myth. I mean, some of you have it applied to your particular ideas as well. We don't have time to go through who created this. These were people, to some extent, who felt that, who were involved with hot fusion and felt that that program was at risk if this turned out to be real. There were academics who could not possibly understand, could not possibly come up with an explanation for cold fusion, so therefore it must be wrong. But there were several that were particularly injurious and effective in creating the myth. One of these is John Huizinga. When Pons and Fleischmann made their announcement, it became a worldwide, it was worldwidely known. It was published in almost every journal and newspaper. It came to the attention of George Bush, the elder. George Bush went to his science advisor, Glenn Seaborg, and said, well, what do we do about this? And Glenn Seaborg, as he has written, essentially said, and I paraphrase, I really don't believe this is real, but we really ought to put together a committee, and they'll look into it, and that'll be the end of it. So the ERAD panel was created. The ERAD panel was already a panel that the government used, and they just created a cold fusion version, a subsidiary of it. They appointed 20 scientists to the committee. Most of them had no interest in cold fusion and had no ability to judge it anyway. They were there purely to make the committee look important. But a few of them did go to the various laboratories and looked into the prospects of it being real. John Huizinga, however, wrote the report. When his co-chairman, Norman Ramsey, read this report, he was absolutely appalled. And he threatened to resign unless the conclusions were made more objective. They were made more objective, but it did not change the tone of the report itself. And as a result, the DOE essentially, officially, determined that cold fusion was not real. Now that had a big impact because no business in the United States would invest money if the DOE would not agree that it was real. Other governments even refused to put money in because, after all, the DOE in the United States said it wasn't real, so why should we get involved? So this was very, very damaging. If you want to know about cold fusion, I suggest there are some very good sources. I suggest you read Excess Energy, Why Cold Fusion Research Prevailed, by Charles Burdett. That's a very good book, an easy read. And if you'll forgive me, I would like you to buy and read my book, The Science of Low Energy Nuclear Reaction. It gives a description of my experience at Los Alamos. It also summarizes all of the work that was known up till 2007. There's over 1,000 citations in the book. I give a lot of background, a lot of understanding of how to do calorimetry. It's just a good book to read if you want to know the science and if you want to try to replicate. If you want to know the present information, Elian RRG is a website that has on it most of the papers, and many in full text, that address the science in the field. It also has a number of essays that describe the science, photographs of apparatus. It's a gold mine because you can search the site using keywords, or you can put it into EndNote and put it into your own bibliography. So it really is handy. A number of other websites have been produced, been created. But a particularly good one is Cold Fusion Now. It has a growing number of interviews with people in the field, and including this lecture today. And Ruby is going to put her video that she's making right now on the website. So if you went to sleep during part of my talk, you don't have to worry. Well, what exactly is cold fusion? It involves several nuclear reactions that produce nuclear products, produces heat. It produces only a small amount of radiation. And that's been a bit of a problem because there's not enough radiation there to account for the heat, nor for the nuclear products. And people say, well, that's because there's no radiation being produced, and that's not true. It's very likely that the radiation is so weak that it cannot get out of the apparatus. But when people have looked for the radiation inside the apparatus, they have in fact seen it. So the beauty of the phenomena is that it does not produce radiation like hot fusion does. And as a researcher, I very much appreciate that. But it does make it difficult to explore the phenomena without that diagnostic tool. And finally, the documented nuclear products are helium-4, tritium, and various transmutation products. And I'll show you some of the evidence for that. And it occurs only in solid environments or in living cells. Now, I'm really grateful that I don't have to apologize for that last one to this group. Normally, when I say living cells, people roll their eyes and figure I've lost it. But I will show you some evidence for that. That the prospect of living cells being involved in nuclear reactions has been known and claimed for the last 60 years. And the evidence is growing very strongly now, thanks to modern technology, modern tools. The other issue is if you have a phenomena that can only be made one single way, then you might be loath to agree that it's real. But if you can make it a number of different ways, then that gives you confidence, because nature very seldom does anything just one way. And in fact, there are 4 different ways in which these nuclear reactions can be produced. Well, science has a number of criteria that it uses to judge whether or not a claim is correct. And reproducibility is one of these, and that's very reasonable. But very seldom is the sentence completed by the right people. And that is, in fact, what happened to cold fusion. After Pons and Fleischmann made their announcement, a number of us were successful in duplicating what they had claimed. But we weren't the right people. The right people were MIT and Caltech. Or MIT put together very quickly a rather crude calorimeter. They studied the effect for a while, published the results, and then had a big party congratulating themselves on having shot down Pond's inflation. It was only a little later that the original data came out, and we discovered that the original data had in fact shown excess energy, and that they had, without telling anybody, shifted everything to zero. Well, when this was discovered, Gene Malov, who was the director of public relations at MIT, resigned in disgust. And he describes his experience in Fire from Ice, the book that he read, the book that he wrote. The other people who were the proper people were Caltech. They did a pretty good job. It was pretty extensive. The calorimeters weren't too bad. They worked very hard. They came up short. They could not produce the effect. And they came up with an idea or a suggestion as to why Pond's inflation had screwed up. And then they used this information to essentially show how incompetent and how fraudulent, maybe certainly how unscientific Pond's inflation were. So drummed them out of the scientific core. It was ironic later on when we discovered how cold fusion works and how to make it work in a reproducible way. People went back and re-examined the work that was done at Caltech and discovered that they had done it in a way that they could not possibly have made any excess energy. They were not using the right conditions. It would not have mattered if they had been lucky enough to get good palladium, which was one of the problems in making it work. It just would not have worked, and I'll show you the reason why a little later. But the damage was already done. The another criteria is consistent patterns of behavior. That means that if you are lucky enough to make something work, and then the next guy is lucky enough to make it work, you should both see the same behavior. You should both see nature behave the same way. And in fact, that has been shown over and over again in cold fusion. And finally, a plausible explanation. For some reason, physicists really are married to theory. They really do like to explain things. And they could not explain cold fusion, and so therefore cold fusion was wrong. Well, let's look at some of the evidence. This is what started it all. This is the results that Pond's inflation published. This is obtained from an electrolytic cell. Electrolytic cell consists of a piece of palladium surrounded by a coil of platinum wire. This is all immersed in heavy water, D2O, with a little lithium dissolved in it to make it conductive. A voltage is placed between the two, such that this is a negative electrode. The D2O is decomposed, deuterium is formed on the surface and reacts with the palladium. Oxygen, of course, is formed on the platinum. Eventually, excess energy is made in or on the surface of this palladium. Now, if you look at the data, you'll see several things. First of all, although the numbers are not very big, they are certainly well in excess of the error of their calorimeter. And you can imagine their calorimeter was analyzed very thoroughly by various people, and they came to the conclusion that the calorimeter was in fact accurate enough to make the claim. You'll notice also that the magnitude of the power that they're producing increases with applied current, and it also increases with the size of the sample. Later work shows that that is a characteristic of the phenomena, and everybody sees that. Now this is a plot of showing the number of times this many watts were produced by studies done. This is a total of 150 studies. And in this particular case, people very seldom study one piece of palladium. And so they many times studied a variety of pieces of palladium. This is the wattage that they reported out of their best sample. And so there's several things you can get out of this plot. First of all, you can see that it's been reproduced quite a number of times. And this was in 2007, there's more now. You can also see that although most of the reproducibility was in the low wattage range, a significant number of significant watts were produced occasionally. This amount of power is impossible to miss, so error is no longer an issue. But the other thing is the shape of this curve. Now let me explain to you how that shape originates. The effect does not occur throughout the sample. It occurs only in special, very rare, randomly created regions in the sample. I call this a nuclear active environment. Presumably, the more of these sites are present, the more energy you'll be able to make. So these samples would have had only a few of these active sites, and these samples would have had a large number of active sites. And this becomes a probability distribution, showing that the probability of having a large number of sites were very low, and the probability of having a few sites were very high. And of course, this extrapolates to zero, having a very high probability. And that's why it's been very difficult to reproduce, or one of the reasons. This is another very important insight. This work was done by Mike McCubry at SRI. They measured the stoichiometry, that is the D to PD ratio, the amount of deuterium that was in the palladium. I might point out that the material here is a deuteride. It's a compound of deuterium, or in other words, it's a compound of hydrogen. It's a face-centered cubic compound in which the all of the metal sites are occupied, but a number of the non-metal sites are vacant, and the vacancy is dependent upon the treatment and the conditions. So this is the 0.88, and this is near 1. So what this shows is that if the composition of the palladium has not reached a critical value, you get no heat. But once it reaches that critical value, the amount of energy that it makes by this nuclear process increases. Well, palladium doesn't like to get to that composition. It takes a very special palladium to do that. And what experienced early in the history was that palladium was gotten purely by accident. You just happened to order something, and it was good, and you used it, and you were happy, and you ordered it again, and it didn't work. So it was pure chance. Now people know to a large extent how to make palladium that will in fact allow that much deuterium to be loaded into it. Here's another pattern of behavior. This shows the excess energy in watts per square centimeter of the area of the cathode against the current density. In other words, the number of amps going through the cell divided by the area of the cathode. You'll notice that regardless of the shape and size of the sample, they all extrapolate to a similar number here, which means that even if you have a sample that is capable of making excess energy, you've been lucky, unless you apply enough current to it, it's not going to show any excess energy. And that was one of the problems with the early studies at Caltech. They did not apply enough current. Some years after Panzer-Fleischmann's announcement, Arata in Japan had a brilliant idea. He said, well, let's see if palladium black, very finely divided palladium, will work. So he encapsulated palladium black, this is nano-sized palladium powder, into palladium, and then used this as a cathode in an electrolytic cell. By making the deuterium on the surface, it would diffuse through, build up a pressure inside, and so essentially you're exposing the fine powder simply to a high pressure of deuterium. The electrolytic part of it is simply there to generate the high pressure. They found that they got excess energy, a large amount of excess energy. And like McCubry at SRI replicated that design and the effect, and this is his data that shows the excess energy obtained as a function of the amount of power being applied. In other words, essentially the pressure that's being created inside for deuterium, and this is for light hydrogen. It does not, nothing happens for light hydrogen to speak of, it's only the heavy hydrogen that works. This is called the gas loading technique now, and it is a technique that is being developed for commercial application because it requires no input energy. It works better if you heat it, but if it makes energy, it will self-heat. All you have to do is put a good enough insulator around it, and you would not have to put any energy in whatsoever. So it becomes, in principle, a source of energy without any input. Well, the big issue was, what if this is a nuclear reaction, what are the nuclear products? And people know the nuclear products from hot fusion are tritium and helium, tritium and neutrons. Those are the two that can be detected. The helium-4 and the protium go off and are not detected, but they're the other products of the pair. Neutrons were not found. In fact, there's a great effort was spent trying to find neutrons. Almost everybody has a neutron detector, so they put it to work hunting for neutrons. Neutrons could not be found. So what could be the nuclear product? Well, helium is the obvious choice, but it was recognized that by conventional models, if it were helium, a gamma had to be given off, and of course a gamma wasn't being given off because people weren't dead. So efforts were made to look for the helium, and quite a number of efforts were made to find helium, and they did in fact find helium. But here's two that made a correlation between the amount of energy and the amount of helium. This is the amount of helium that should be detected, that is the helium to watt second, or the amount of helium to amount of energy. That should be based upon the mass change in going from 2 deuterons to a helium. And this is the data. These are two different data sets. The open circle points were made first. They have a somewhat larger scatter. That was done with an isoparabolic calorimeter. Later, somewhat better work was done with a Seebeck calorimeter, somewhat less error. But you'll notice that they are in basic agreement, but they're all lower than what's expected. They're lower on average by a factor of 2. And that fits with how we understand the process to work. The process takes place on the surface of the cathode. The helium made there has two choices. It can diffuse inward and be captured and not detected, or it can diffuse outward towards the surface. It'll go off then as a gas and then be detected by the later analysis. And there's a 50-50 chance of it going in either direction. And this fits perfectly with that concept. Tritium is also made. Tritium, as you all know, is a radioactive isotope of hydrogen. It has a half-life of 12.3 years. It does not exist in nature, except what little's left over after atom bomb test and a little bit that's made in volcanoes. But nevertheless, it is not a common material for contamination. We at Los Alamos made an effort to look for tritium. I was in a group that were populated by experts in tritium, for other purposes I might add, but nevertheless, they knew tritium when they saw it. And we discovered that the tritium was made only after a delay. A similar delay was always required to make the helium, I might add. These nuclear reactions do not occur without an investment of a certain amount of patience. Nature's like that, you know. I mean, it really makes you work for it. But once the reaction starts, the tritium content grows quite dramatically, and then quits, and then it slowly goes away. This was a similar kind of measurement made at Texas A&M. They found that also they had a delay, but when they increased the current, the rate of production went up, and they increased the current again, and it went up again. Similar to the way helium is made, or the heat's made. It's sensitive to the current. And you can see here the cell running at the same time showed absolutely nothing. So the production of helium and the production of tritium match one another in their characteristics. Tritium has also been made by the gas discharge technique, not just by the electrolytic. Here, this is work by Tom Claytor. Tom Claytor started this work at Los Alamos National Laboratory and was supported by the laboratory for many years before the DOE got wind of it. And now he's working on his own in his own laboratory on his own nickel, but continuing to explore this phenomena where you simply place a low pressure palladium or low pressure deuterium into a container. Electrodes inside, place a voltage between the two electrodes, and you get a discharge. If the cathode is made of a particular material, you'll get tritium. And the kind of material is very, very important. Only certain materials work and some do not. And here's an example of a material that worked, and here's an example of a material that did not work. This measurement is made in situ while the process is going on, while the discharge is going on, using the radioactive decay of the tritium as a diagnostic. Transmutation is also one of the products that's confounded explanation to some degree, and that evidence has been growing steadily. But it's an evidence that is more difficult to justify, to prove, because there's always a possibility of contamination, and the amount is always very, very small. But here's a study that was done at Mitsubishi Heavy Industries in Japan. They created a sandwich that consisted of alternate layers of thin layers of palladium and calcium oxide deposited on a piece of palladium, about 1 millimeter thick. And they heated it slightly and passed deuterium through the sandwich between a pressurized gas into a vacuum. They had an X-ray beam on this side so that they could interrogate the surface and see what was happening to the elements in the surface. Well, then they deposited various elements on the surface by various techniques, and these elements were either barium, cesium, or strontium. When they put barium on, they discovered that samarium grew in. The barium went away, and the samarium grew in. And in this case, because barium has several isotopes that don't match samarium, they could see the abnormal isotopic ratio growing in the samarium signal. So there's no doubt that they were converting barium to samarium. Well, that requires 6 deuterons to go into the barium. And they have to go in simultaneously. You can't go in one at a time, because then you get a whole string of different transmutation products. They saw only one. When the cesium was used, they got praseodymium, and when the strontium was used, they got molybdenum. In this case, 4 had to go in this case, 4 had to go in. This is similar to what other people see, but when it's done in a more or less general environment where there are a lot of different elements, you don't know which one's producing the product. And so it's a little more ambiguous. This study is not ambiguous. It's being replicated now with growing success in Japan, and an attempt was made at NRL here in the United States that was not very successful. Well, let's talk a little bit about living systems and their possibility of making nuclear reactions. This is work that's done in Russia and the Ukraine. They created a cell in which a bacteria was placed, and they had to choose a bacteria that would grow in heavy water, and there's not a lot of those, but they found one. And they mixed in with that heavy water manganese sulfate, and they looked for the production of iron 57. And they used a very clever technique. They used the Mossbauer effect. Cobalt 57 gives off a gamma that is absorbed by iron 57 if the energies match exactly, and the energies can be matched by producing a Doppler effect on the gamma ray by vibrating the source. And they were able to show the iron 57 growing in over time. They got the reaction rate totally unambiguous. There is no other element that has that ability to absorb that gamma ray. It's totally unambiguous. The only issue is whether you believe them. And this hasn't been replicated, so that's always an option. A not very likely option, but nevertheless, that's the only back door that a skeptic has. They used light water, it did not work. They used something other than magnesium sulfate, it did not work. Well, then they got the idea, all right, so let's say we can make a transmutation reaction using bacteria. Perhaps they will also change the radioactive decay rate. Now they have a big incentive there. They have Chernobyl. And somehow or another they got to get rid of all the radioactivity that's going to take many, many years to decay away. So if they could speed up that by using bacteria, they would have a real winner. And that's apparently what they have now. They have, this is a graph of the number of days against the intensity of the radiation, logarithmic value of the intensity of radiation, for a mixture of barium and lanthanum that would typically come out of a nuclear reactor. This is radioactive. It normally decays at this rate, and in the bacteria, it decayed at this rate. So clearly the bacteria were having an effect on the half-life. They did the same with cesium-137, which is also a gamma emitter, has a 30-year half-life. They were able to speed it up by a factor of 5. They found that the particular bacteria that they used was important, and the more varieties of bacteria were in the culture, the faster it would work. By conventional thinking, this is absolutely impossible. The original work was done using heavy hydrogen. Now, thanks to Rossi, and I don't know if any of you have heard of the,
Bring on them.
okay, Anyway, he has brought to the attention of the scientific world the value of light hydrogen. And before that, Piantelli also was working in the light hydrogen field, but was fairly ignored. He was using solid pieces of nickel, whereas Rossi went to fine powders. Rossi increased the reaction rate, the production rate of heat by orders of magnitude. But this is the data that Piantelli published, which is readily available. Rossi's data is not so easily available, so I'm not using it. But here is the energy that's applied to a rod of nickel that is in a pressurized hydrogen atmosphere. This rod of nickel, if nothing's done to it, its temperature would follow this line here. This is the temperature difference between the inside and the outside of the container. But if they've treated it in their special way, this is the temperature that you get. And this difference is the extra energy that's being made by the nuclear reaction within the nickel. Well, when he did this, he also discovered that radiation was produced. And a very clean, very well-documented radiation was being emitted from his cell. Rossi is seeing also radiation and has to put lead in to protect the people around from the consequences of that radiation. But apparently the light water system makes easily detectable radiation, whereas the heavy water system does not. So there's a difference in the energy of the radiation, but I would argue not a difference in kind. This radiation is generated by photons. Well, so what's the present situation? I mean, other than the fact that normal science doesn't believe this. I mean, we'll not have to point that out. It's too depressing. But from our point of view, the claims have been replicated hundreds of times in laboratories all over the world using 6 different methods. That should be enough to get people's attention, one would think. The power production has reached commercial levels at this point. People have been having a hard time believing Rossi, but that's another issue. Laboratories are exploring the effect in at least 8 countries now, and several that are getting increasingly interested. There have been a series of conferences held, starting in 1990, the International Conferences in Cold Fusion. The 17th of that series is being held in South Korea in August of this year. South Korea wants to get into the game. Russia, Italy, Japan, China are already heavily in the game. A plausible explanation has been proposed, and we'll talk about that a little bit later. And this is an ideal power source that has the potential to change society as we know it, because the cold fusion phenomenon can be made to occur in a small system. It could be a system that every house could have. That system would not possibly be the size of a small refrigerator. It would supply all the power that you would need to heat, cook, lights, and charge your Prius. So it would provide you with all the energy that you would possibly need for practically nothing, because it uses just light hydrogen and nickel, or perhaps the later versions might use heavy hydrogen, but getting heavy hydrogen is a trivial operation, and it's also clean. It doesn't produce any contamination. So, of course, it would take over from all the other power sources, which of course would cause them great consternation. And that's part of the reason I suspect that people aren't jumping on board. So why should you care? Well, I mentioned a few of the reasons. We need energy. We're using energy that's causing all kinds of harm. the energy is costing us a tremendous amount of money. We're even willing to risk the food supply to save a few bucks. Instead of buying oil, we buy ethanol. And modern society will eventually come to an end without another energy source, because we will eventually run out of the present carbon-based energy. We'll run out of the present uranium-based energies. And solar and wind simply are not big enough to do the job. So society will in fact come to an end, and that's the only justification that has been made to support the hot fusion program. People knew that it was going to be very, very difficult and very expensive, but there was no other choice. You either try to make that work, or society eventually goes down. Well, now cold fusion's come along and changed the equation. Well, now we get to theory. Theory for me is an awkward subject. There are hundreds of theories. A few of them have bubbled up to the surface of the cauldron and are getting more or less universal attention. All of these theories have been developed by physicists. When I try to explain their theories, they are not too happy because I'm not a physicist. And what's worse, I don't think any of them are correct. And that might be the real reason why they're not too happy. But I won't go into the various theories that have been proposed and explain to you why I think each one is wrong, because there is a universal reason. All of these theories are applied to the lattice itself. For example, they're all applied to the palladium deuteride structure. A chemical lattice is not like a plasma. Chemical lattice has rules of its own. The electrons, the nuclei, all have roles that they have assumed in that lattice, and it's those roles that have created that lattice. And we know that the lattice, unchanged, does not support a nuclear reaction. So some kind of change has to take place in that lattice. And I argue that such a change is impossible in a chemical lattice, because the chemical lattice, the conditions that created that lattice, will fight that change. And every chemist knows this to be true. Obviously, not every physicist knows this. But whatever the explanation is, it has to explain certain facts. The facts are the helium-4 must be produced without significant radiation. So the problem is, how is that energy dissipated? It has to come out into the lattice, but not as energetic particles. The energy in nuclear products and detected radiation are not neutrons, and they result from either the light hydrogen or the heavy hydrogen being present. Both of them work. Many of the theories will not explain how the light hydrogen can work. Tritium is produced without significant neutrons or radiation under the same conditions in the same environment as is the helium. So they obviously have a relationship to one another in the explanation. Helium-3 is not produced as a primary product, which would result quite naturally from a PD fusion. Helium-3 is seen as a decay product of tritium, though. Transmutation occurs when either D or H are present, and the nuclear reactions occur only in special sites. So these are the conditions that have to be addressed, and most of the theories simply ignore one or more of these conditions. And that would be another reason why they have been unsuccessful. So I gave a considerable amount of thought to this and asked myself, well, okay, it can't occur in the lattice, it can't occur in the chemical system. Where could it occur? It has to occur in something that is present no matter what method is used, no matter what material is used, no matter whether it's light hydrogen or heavy hydrogen, it has to be something that is universally present in all of the experiments that work, but not in the lattice. Well, the only feature that is universal are the presence of cracks or voids. Now that seems crazy because for a long time in the field, people felt that cracks were bad. They allowed the deuterium to leak out of the palladium. And so they were ignored, or people were trying to avoid them. But cracks really are the only locale that could support it. And what I propose is that the crack has to have a particular size. And when it has that size, it allows the nuclei of either a deuteron or a proton to come into that and set up a series of, let's say, proton, electron, with the electron being between each of the nuclei, thus hiding or reducing the Coulomb barrier. Now, that electron has to have very special properties, and that's the only thing that is novel. This is total, consistent, normal physics, except for that electron and its characteristics. So something new has happened, has been discovered, is required to make cold fusion work. But if we accept that electron being present, then we can make some predictions. If you have that series and all of them are protons, this will condense down by giving off X-rays, or protons if you wish, because these are produced by a resonance of the structure. Those protons are coherent, and so we have an X-ray laser. Evidence for that has already been seen in some of the data. But as this condenses down, gives off more and more energy, it eventually becomes a deuteron, or a series of deuterons. If deuterons are present, they condense down to helium, and if you have a mixture of deuterons and protons, they condense down to tritium. Now, I won't try to go into the details of this. Those are slowly being developed. I have several papers that describe it, but a great deal more work has to be done before this can be justified. But right now, from my point of view, it's the only explanation that accounts for every single observation, and is not consistent, it's not inconsistent with anything fundamental, such as the laws of thermodynamics, or having a nuclear reaction occur in a lattice itself. Okay, but in summary, Elian R is real, can be a source of clean energy. It may provide a way to decontaminate soil, gives new insights into the nuclear interaction, the role of the neutrino. I haven't talked about the role of the neutrino, but this has a direct bearing on the standard model of nuclear behavior. Elian R may be a source of coherent X-rays, and it raises questions about how science evaluates new discoveries. Because of the discovery this important can be ignored this long, something is desperately wrong with the way the system works. Thank you.
Okay, we've got 10 minutes before we need to be out of here, but let's do 2 or 3 questions. And okay, Jeff, you want to? Oh. All right, yeah, let's make it just 3, and then we'll need to close it out.
Hi, my name is David. Question for you. You mentioned about cracks and cavities. Any idea in terms of order of magnitude of the size of these cracks? So, like, is that around like 10 to 50 nanometers, or any ideas?
Well, the size of the crack is something that will have to be determined. They have to be small enough that they would not allow the hydrogen molecule entry, because we know the hydrogen molecule does not produce a nuclear reaction. They have to be big enough that a single nucleus of hydrogen can go in there and be retained and not interact with it in such a way as it would in a chemical state. So I'm guessing something in the less than 10 nanometers.
Less than 10 nanometers? Okay, thank you.
Yeah.
Along those lines, I see a lot of parallels with catalysis reactions here. In all cases of surface reactions and catalysis, eventually you have a deactivation component. So is there any evidence of this, especially when dealing with these palladiums and nickels, hinted toward the surface area effect of the nickel because you increase the rate with surface area? So if there is some surface interactions, is there any deactivation over time?
Well, I don't know which kind of deactivation you're talking about. There's the deactivation that occurs as the photons are given off. That's the way in which the energy is dissipated from the nuclear reaction itself. But now, within the lattice, all kinds of chemical interactions are taking place, and one of the things you have to realize will control the rate of the nuclear reaction is the access of deuterium or hydrogen to that site. And so now it has to diffuse through, it has to interact with the surrounding chemistry in a conventional way. Now, the electrolytic cells typically die. They do not live forever. And so you can say that there is a deactivation of some sort, but I think that's caused by the destruction of the necessary cracks.
Charles Lucas. My son and I have developed a new electrodynamic model of the atom and the nucleus, and we explored this question as to where the cold fusion is occurring. And in the model that we have for the atom, we use a ring electron, which is a finite size electron, and we were able to produce more atomic data for hydrogen, more emission spectra lines than any quantum model has ever produced before. We were able to predict 64 emission lines in the extreme ultraviolet, and the standard direct quantum model predicts 0 of those lines. So we were looking to see where this might occur, and we thought the cold fusion was occurring at the atomic shell level for electrons. And our electrons are magnetic, and we measured the strength of the magnetic force for various shell sizes when you add the last electrons or charged particles to the shell. And we found that some of the larger shells are extremely strong enough to produce nuclear fusion. And so we think, although we've not done a whole lot of work, we think that this may be occurring in some of the larger shells of the atom because of the magnetic properties of the electron. And your crack also kind of supports that idea, because you've got to be able to get access of these products that you want to fuse together to the atom at the right place. And so you need that kind of access. And you're probably going to fill it up after a while with some of these products, so that you won't be able to do it anymore on that atom, because you'll capture some of this material. And it's going to take your excess energy into the atomic shell.
Well, you're seeing radiation that's in the neighborhood that Randy Mills has proposed results from hydrino formation. Do you know that that's not the source?
Say that again.
Randy Mills, are you familiar with
Yes,
Randy
I'm
Mills'
familiar
hydrino?
with Randy Mills.
The hydrino, he says, gives off radiation in the extreme ultraviolet.
Yes.
And it sounds like it's in the same ballpark that you're looking at.
Well, his model is different for the electron. He has a spherical model for the electron where it precesses as it goes around.
Yeah, you have different models, different theories. I'm just addressing the experimental observation that you saw. And the issue would be whether you and he are seeing the same thing experimentally. He has one explanation, you have another.
Right.
And so you might want to get together with him and find out whether you're looking at the same thing or not. But the other issue, too, is that if you have a special electron, that special electron has to be able to do two things. It has to be able to overcome the Coulomb barrier, and you're claiming that yours will. But then after that happens, the energy has to be dissipated in a way that is invisible to people who are doing the experiment.
And we're claiming that the shell is bound magnetically and has the ability to absorb that energy.
Well, I don't know which shell you're talking about, but if
the
you make
shell of
helium-4, you have those shells.
Yes.
And they cannot take up 24 or 23.8 MeV. So you have, for each helium that's made, you have to dissipate 23.8 MeV somehow or another. And you
Robert,
can't
you may be able to pass that on to the lattice through this magnetic cover.
Well, that's one of the theories that have been developed trying to do precisely that, but that's a real challenge, which I don't think has been met.
Okay. Well, I just wanted to suggest that might be a possibility.
Sure.